So let us move on to the next module, which is based on game playing. We have seen in previous classes that game playing is a perfect example for studying artificial intelligence due to its strict rules and regulations over the games and huge number of states available in between the start of the game and finish of the game. Again, we will be having definite outcome on the conclusion of a game, which should be a valid outcome. So due to these situations or values, we will be considering a game application as a perfect tool for studying artificial intelligence. So games can be of different types, which are played between two persons or multiple persons, or it can also be a one-player game. Solving a Rubik's Cube or a jigsaw puzzle fall into a one-player game, while games like tic-tac-toe or chess or checkerboard all belongs to a two-player game. So we'll be concentrating on two-player games rather than one-player game. Then again we can categorize these games as perfect information games and non-perfect information games. In a perfect information game, when one person or player knows the movements of or status of the other person's situation, it is called as perfect information game. While we play a chess, a player A can see the coin positions of player B. Similarly, player B can also see the coin positions of player A. So those informations are known to both the players. A board information is known to both the players. Such games are called as perfect information games. In games like playing cards, the person who is holding cards will not show the card positions or what is having in his hand to the opponent. So both of them will keep hiding their cards, the details about their cards. Such games are called as non-perfect information games. Here again we will be considering only perfect information games for study purpose. Then we are having zero sum and non-zero sum games. In a zero sum game, we have only two options. While one is winning, it is sure that the other will lose. So when there are two opponents, when I win, you lose. That is the only condition in zero sum game. But in a non-zero sum game, we are having three options. Either one will win, or the other will win, or both can win or lose, or a draw condition. Such games are known as non-zero sum game. So if we are putting these in a nutshell, we can say that game playing uses intelligence, searching algorithms, logics, etc. to defeat the opponent, and it can have the result as a win, a loss, or a draw. Since there are several actions and counter actions to be applied on these proceedings of the games, game playing is an important topic in artificial intelligence because it is having a well-defined rules and laws for evaluation purpose, and there are games which involves luck too, but we will not be considering this luck factor into account for the studying purpose. We will only go with the rules and laws of evaluation. Normally in artificial intelligence, games played between two players are being considered. So the main aim of player 1 is to win, and that of player 2 is to prevent player 1 from winning. So this has to be taken seriously. One player will be aiming to win the game, but the other player will be aiming to stop this player, his or her opponent, from being winning. In that process, the second player may also win, defeating player 1. So that is the aim of these two players. In other words, player 1 maximizes the chance of winning and player 2 minimizes the chances of player 1. So we will be considering with respect to one player only. If we are considering player 1 as the first person, then the chances of winning will be maximizing player 1. Then the state of player 2 will be minimizing the chances of player 1. It can happen the other way also. We can take player 2 as the maximizing agent. Then in that case, player 1 will be the minimizing agent. So we'll be using two major algorithms. One is the min-max algorithm, which you are familiar with. We have seen to it in semester 1 while we were studying a min-max heap, and the next one is alpha-beta pruning for solving this game problem. So there are two algorithms, min-max algorithm and alpha-beta pruning, for solving game problems. Then again we have seen that we can represent the states of a game in the format of a tree or a graph, and these are some of the graphs which we have seen in previous chapters. This is a state space tree of tic-tac-toe. Then this is the state space tree of puzzle. This is another state space tree of 4-queen problem. And these trees are not complete. We are having a bigger nodes, because in a 4-queen problem we will be having 4 states from this root. We have shown only 2 of them, so this will be bigger in size. So as the number of states increases, we will be having a bigger sized tree. So these trees are called as game trees. We can represent all possible states with a directed graph or a tree, which is known as a game tree. The nodes of the graph or tree represent the states of the game, and the arc or edge represent possible moves or state changes that is allowed in the game. The game playing programs depend on game tree searches to find the best moves for the current position. Let us see an example. Consider the start of the game as the start state. Then if we are representing like this, say S1, S2, S3 up to Sn, this means that at state start we are having this much of possible movements, valid moves, which produces equal number of valid states. So if we are selecting an operator M1, we will be getting the state S1. Then operator M2, will take us to state S2. Likewise, we can have n number of operators corresponding to n number of states. And on these states, we can also perform other activities which are allowed by the rules and regulation of the game, and we can explore this state into different states which follow this action M1. So from S1 also we can have different branches. If there are 5 or 6 operators at S1, we will be getting 5 or 6 succeeding states. This can be continued in all these states. And this process is continued until when we reach to a goal state or termination states, which will be the leaf nodes of this tree. So those leaf nodes can represent either a win or a loss or a draw. So in normal cases, the size of the tree will be very large because there are huge quantity of states, valid states, when a game is being played. So the size of the corresponding tree will be very large in size. Then these are all some technical terms. The ply of a tree. Ply means the edge we are going through to the next state is known as a ply. And if we reach to a leaf node with 5 plies, if we say like that, we can say that from root to the leaf we have 5 edges. So these are some technical terms. You have seen these in the first semester. So let us see or revise the min-max rule, which says that we will be having a min level and a max level alternatively. So the player, each level, alternate levels are being represented by each players. Suppose we take this example. This is a state and it is having 4 valid operations or moves which produces these 4 states. So if this is a maximizing player, then these are the corresponding values being assigned to these states: plus 10, minus 3, minus 7 and plus 3. A maximizing player has to select only one of these moves. He cannot go with all the states. Naturally, he will select the maximum value. So among these, the maximum value is 10. So a maximizing player will be selecting A as the valid move or his selection move. If this is a minimizing player, then naturally the minimizing player's aim will be to minimize or take the minimum value, which happen to be minus 7 among these values. So that player will be selecting only C as the next move, so that the maximizing player will be getting only this minimum value. So this will be continued towards different levels. So let us take one more level. So this is the initial state. We are having 4 moves or 4 states, which is a maximum level, and this is a minimum level. So we will be always moving from leaf to the root, and while moving from leaf level or the final level to the top level, we will be taking values to the upper level based on the level which is a minimum or maximum. If this is a minimum level, then it will pass minimum value among these. This can be more in number. Then its parent will be getting only the minimum value among those children. So here A will be getting -3 because this is a minimum state. So it will be pushing minimum value to the upper level for the maximizing player, because the aim of the minimizing player is to give minimum values to the maximizing player. It can happen in the other way also. If this happen to be the maximizing player, he will be providing the maximum value among these child nodes to the minimum player. So as with this example, this is the maximum level and this is the minimum level. So A will be getting, state A will be provided with the value -3 because the minimum between +10 and -3 is -3 only. Here we have only one value, so naturally it will go to the top, or B, which is +1, and C will be getting minimum values +3 and D will be getting -3. So the values will be -3, +1, +3, -3. And the maximum value among these values will be +3. So maximizing player will be selecting C as the choice which will be put in this route. So in this way the min-max algorithm works. So these are the explanations. We have seen this in first semester. This is only a revision. I am also providing a video about this min-max algorithm.